of the definite integral. And then we can go back and spread my papers all over. What's going on here? Then we can go back to that example and estimate it. I didn't have a page 4. Did I jump over page 4? Very possible. This must be page 4. Yes, it is. Okay. So after we looked at the properties of the definite integral, I would like to estimate that. Okay. So let's look at the first property. Let's say we have a function, and this is f of x, and this is a, and I would like to determine the integral from a to a from f of x dx. What do you think this equals to? Anyone?
Will it be 0?
Of course. There is no interval that I can split into anything. So of course it's 0. It must be 0. Perfect. Here is the second property. The integral from a to b from f of x dx is the same with the opposite from b to a from f of x dx. Next property. We already used it. So the integral from a to b from a constant times a function dx, of course, the constant a to b from f of x dx. For an odd function on a symmetric interval, odd function and symmetric interval. I'm going to graph an odd function right now. Here it is. On a symmetric interval, let's say, between negative a and a. Both conditions have to be fulfilled, odd function and symmetric interval. What do you think the answer would be? Any guess?
0.
Excellent. Of course. They're identical. One is negative and one is positive. Great job. 5. Even function. And symmetric interval. Here's the graph of an even function between negative a and a. If the interval is not symmetric, we cannot use this property for either one, of course. So then the integral from negative a to a from f of x dx, if the function is even, the answer would be, I'll help with this one, twice the integral from what?
Zero to a.
Right. And this is so much easier. You don't want to plug in the function negative a. It's so much easier to plug in 0. So yes, we like that. Whenever we notice that the function is even and the interval is symmetric, we would like to change this into this immediately. Good. Let's look at the next property. Here's a function. Here's A, here's B, here's C. And I want to determine the integral from A to C from f of x dx. We know that the definite integral is a limit, so it's the same procedure. What do you think this will equal to?
The integral a to b plus the integral b to c.
That's it. And of course, and vice versa. Right? So it goes back and forth. 7. The integral from a to b from f of x plus or minus g of x. We used this in so many different situations before. So what will the answer be?
The two separate integrals.
Exactly. Yes. Do not forget, the integral has to have a function even if it's 1, and it has to have the differential of x. If it's plus, it's plus. If it's minus, it's minus. Next property. The integral from a to b from a constant dx. The function is just a constant. That's what it is. And you can say, okay, take it in front. Fine, I'll take it in front. So now the function becomes 1. Okay, let's say I don't know what that is. Although I do. But let's just graph it, and then we'll continue it. I graph the function. What function? 1. I graph the interval. That must be the area. So I copy the C, and then what do I copy? Can anyone give us this area? Base times height. Base times height. It's a rectangle. What is the base?
A times b. A plus b. B minus a.
B minus A. But we know how to determine that. We don't even need to look at the graph. Let's determine it because we know. So we want to determine integral from a to b from a constant dx. And we know that the constant goes in front from a to b dx. And so this is C. Which function prime is 1? And I have to evaluate it from a to b. function prime is 1. There is only one x indeed. So like before, I plug in b, and I subtract when I plug in a. Exactly the same thing. Okay, which number am I? Number 8. I have to look at 3 more. Number 9. If I know that the function is always positive, like the previous example that we looked at, even the one that we just graphed at the beginning, this is not a positive function always. It's positive and then negative. But if I know that the function is always positive, what do you conclude about the integral from a to b from f of x dx? What should that be? Of course, we are looking at the interval a comma b. What type of number we expect if the function is never negative, never under the x-axis? Yes, or 0. That's common sense. Number 10. Let's look at the graph. Here's the interval a comma b. And I have a function f of x. And I have a function g of x. Obviously, the way I graphed it, would you agree that f of x is definitely greater than or equal to g of x on a comma b? I don't know, outside of a comma b anything can happen, but do you agree that between a and b, the function at the top, f of x, is greater than the function underneath it?
Yes.
Okay, then what do you think is going to happen? Obviously, the area under the graph of f of x must be higher than the area under the graph of g of x. So I'm going to write it one more time. The integral from a to b from f of x dx must be greater than or equal to the integral from a to b from g of x dx. It must be the case. And I promise the last one. Very similar to the previous one. Here's another situation. Can I say that on the interval a comma b, according to my graph, f of x is between lowercase m and uppercase m?
Yeah.
So therefore you would agree, I'm sure you will, that this area is smaller than this area, which is in turn smaller than this area. So the integral from a to b from m dx, the integral from a to b from f of x dx, without the x the integral does not exist. The integral from a to b from m dx. So this must be the relationship between these three integrals. So the middle one I cannot calculate if I don't have the function. But these two I can. And we just did a few minutes ago. So this is the integral from a to b from f of x dx. Can anyone give us this or this? We just did the same thing, but we had c instead of m. And that's it. And these are the properties, and we can work with them now. So what do you think?
And having feet on the side.
That's it. Very good. Yes, because these are just based on height, right? These are rectangles based on height. Okay. We went through a lot of properties, so let's see what we can work with. Okay, I would like to look at problem 47, page 384. The integral from -2 to 2 from f of x dx plus the integral from 2 to 5 from f of x dx, sorry, not plus, I'll erase that, minus the integral from -2 to -1 from f of x dx. They want us to condense this into one integral. So let's take a look at the intervals. So we have from -2 to 2, this is one piece, and then from 2 to 5, that's the second piece. But now they want us to subtract this piece. So if we just condense these two, we have between -2 and 5, because we have between -2 and 2, and we have between 2 and 5. So these two are basically the integral from -2 to 5. But they are asking us to remove the integral from -2, or the area between -2 and -1. So then, when I condense the whole thing, what will I write? I don't know, were you able to see what I was showing? Sorry, maybe not. So, were you able to?
No.
So sorry, so please always stop me, because I can't look at the computer on my left and the computer on my right and also right. My apologies. So these two integrals are basically this, from -2 to 2 plus 2 to 5. But then they want us to remove the integral from -2 to -1. So this is what we are left with, between -1 and 5. So this is the integral from -1 to 5 from f of x dx. Does it make sense? Is this okay? Okay, that's one property. I would like to determine 50. We are asked to find the integral from 0 to 5 from f of x dx. And we are given the function f of x as 3 for x less than 3 and x for x greater than or equal to 3. How do we do this? Any suggestions, any ideas? Any ideas? Well, in order to determine the integral from 0 to 5, there is a break at 3. So the integral from 0 to 5 from f of x dx must be the integral from 0 to 3 plus the integral from 3 to 5. Which function from 0 to 3 dx and which function from 3 to 5 dx? From 0 to 3. Very good. And then x. And we know already how to calculate these. We learned that. Like with the L'Hopital's rule, I couldn't wait till chapter 4 because we were able to use it in chapter 3. The same thing here. The fundamental theorem of calculus is in 5.3. But why? When I can use it right now. So that's why we already talked about it. Okay, so which function prime is 1? Because I take 3 in front. I'm allowed to as a constant. So then 1. Which function prime is 1? And that will be evaluated from 0 to 3.
X.
Very good. And then here, which function prime is x? And that will be evaluated from 3 to 5. Remember, we increased the...
1/2 x squared.
Very good, awesome. We increase the power by 1, and we divide by that result. Good. So when I plug in 3, I get 3 times 3, which is 9, but when I plug in 0, that's gone. That's why I like 0 here. Now when I plug in 5, let's leave 1/2 outside. When I plug in 5, I get 25, minus when I plug in 3, I get 9. So this is 9 plus 25 minus 9 is 16, so 1/2 times 16 will be 8 plus 9 will be 17.